Alright, we're still in Module 3C, and we just discussed the chain rule for determining a derivative of a composite function, and in this module, or in this video I should say, we're going to focus on the other half, partial derivatives. So now we kind of expand our definition of a derivative from being in a single variable function to what we call a multivariable function, or just a function where there is more than one independent variable. So for example, we are often going to deal with a function z that is going to be a function of x and y. Okay, and so we can still differentiate a function z, but we can only do one at a time. We can only differentiate it with respect to one variable at a time. So we either have to choose x or y. Okay, when we do this differentiation process, the other variable will be treated as constant. Okay, so if we're differentiating with respect to x, we think of y as just a number, as a constant. Okay, and when we do this derivative, it's called a partial derivative because it only communicates a partial change in the dependent quantity in z, right? Because there's still, since it's a function of two independent variables, we only determine how it's changing with respect to x. There's some influence from y, we just aren't able to determine it right off the bat. Okay, and so we have a little bit of notation to work with. And so the partial derivative of z with respect to x, and this is where the language comes into play more so than before, and we're going to be very particular with our language here. So the partial derivative of z with respect to x is denoted by, and now we have a curly d over z, curly d over x. This curly d, I was told to pronounce it as del, D-E-L. So this is read as del z over del x is equal to, and then f, the function. And the other way to denote a partial derivative is to use a subscript of the original function. So del, and then this is f, partial of f with respect to x of x and y. And you may also see it written as just z subscript x. And that's another way to communicate the partial derivative. And then so the other partial derivative for this particular function is del z del y is f sub y of xy, and you could also write this as z of z sub y. Okay, and for as many independent variables you have, that'll be how many partial derivatives you can find. Okay, and now also keep in mind, and you'll see in your professional problem for Module 3, is that you can continue to do partial derivatives just as you did higher derivatives back in Module 3b, and essentially the process is the same. But that's more to come on that. So if we go ahead and have this function, we have z is equal to all this good stuff, and we want to determine the partial derivatives, and we're going to assume that we're in the domain of the function z so that we don't run into issues with differentiation. So if I do the partial of z with respect to x, and again you could denote this just as z sub x, this will be equal to, and now I want to make a note here. So when we do this, this means y is constant. So I think of y as just a number. Alright, so when I go through this, well, let's look at this thing first. Okay, so I have this. This is now a constant, and this is a constant. Okay, so what I'm going to do is maybe what I'll do before I actually do the derivative here is actually just rewrite it and regroup it. So if I do that, I'm going to write z as, if these are both constants, I can write this as 3 square root y parentheses x cubed minus x, and then plus, and then now I'm just going to group this, and I can add parentheses wherever I want with addition, y squared plus 1, because that's all a constant. Okay? So if I differentiate this, just looking at this, this is all a constant, so I just rewrite that. Okay, let's see, I'll leave that back in. And so this is 3 square root y, and this is a power rule, so I multiply by 3, and then the rest becomes an x squared. And then subtract 1, again by the power rule, and then this is all a constant, so I'm done. Okay? Now, looking at the other derivative, del z del y, which is, I can write that as just z sub y. Alright, and if I regroup this now, this says that, well, x is now constant. So if I regroup this, alright, regrouping z, now this is constant, so I'm going to put a parentheses around this, so I know to keep that all the same, square root y, and then plus y squared, and then I add to that, and now the 1 and the minus x are constant, so I'm going to have 1 minus x, just rewriting it a little bit. Okay, so now I want to differentiate this. So the 3x stays, or the 3x squared, or 3x cubed, sorry, stays the same. Derivative of the square root of y is times 1/2 y to the minus 1/2. And then the derivative of y squared is 2y. And lastly, that's a constant, so I'm done. Okay. Partial derivatives, again, think of whatever variable that is not in your derivative that you're not differentiating with respect to as constant. Okay, application problem. We have Z being profit, and profit from selling blood pressure cuffs. Profit depends on the number of devices sold, okay, which is X, and the cost, which is in Y. Okay, we want to find the partial derivatives and evaluate them for 200 devices sold and $100 cost for production. And then we want to interpret the evaluations. Alright, so let's go ahead and do the derivatives. Del z del x first. Okay, so again, this means that y is constant, so anytime I have a y, I don't worry about that. Or a term containing only y, I don't worry about that. Alright, so let's just go ahead and progress through this thing. So derivative of this has an x power rule. I get minus 5x to the fourth. This term, the second term, contains only y, so that is a constant, and derivative of a constant is 0, so I ignore that part. Then this last part, I have y to the x power. Well, that's an exponential expression because x is in the exponent, so this is plus, and the derivative of this is ln of y times y to the x. Okay, and I think I'll come back and do the evaluation in a minute. I want to get through the derivatives because that's the first part here. And so doing the other derivative, del z del y, alright, progressing through this thing, x is now a constant, so this first term, constant, derivative constant is 0. Leave that alone. This one is an exponential expression, so the derivative of that is going to be natural log of 3 times 3 to the y. And now this plus y to the x is a constant, and so this is just a power function, and that is going to be plus, let's see, an x, bring the exponent down, times y to the power of x minus 1. Alright? So now, I found the partial derivatives. I need to evaluate them, but carefully because it says x is in hundreds and y is in hundreds. So really this is saying del z, del x evaluated at, and I'm going to use coordinate form, cost is y, and that's, okay, so this is really at 2 comma 1. And so if I evaluate this, and I'm going to skip writing out the computation, but if you punch this into a calculator, I got minus 80, and let's go ahead and add the units. So this would be dollars, again profit is in thousands of dollars, per, and then the unit of x is per 100 devices. Okay, and similarly down here, if I do del z, del y evaluated at 2 comma 1, so this means an x value of 2, y value of 1, I get 5.3, and this is kind of a funky unit, but this is going to be actually this should be thousands. This is going to be dollars, and then this is thousands of dollars per, and now the unit of y, that was in hundreds of dollars. So like I said, it's a little weird for the units, but you should still label them. And then the last part of this problem says interpret the evaluations in context, and really by doing the units that's all you need. But here we can say the rate of change in profit due to the number of devices sold in hundreds is this. So, and I'm not going to write this one, but I'll just say the rate of change in profit due to number devices sold is minus 80 thousands of dollars per 100 devices. Okay, and the other one would be similar, the rate of change in profit due to the cost of production in hundreds of dollars. Okay, similar. So again, partial derivatives, the idea is you have a multivariable function and you are trying to determine the rate of change in the dependent variable due to the various independent variables, and you can only do one variable at a time, which is why you have to hold one variable, or you differentiate with respect to one variable, holding all other variables constant. All right, so we'll get some practice with this in class and web work and such. So stay tuned, and that's a brief introduction to partial derivatives.